Good afternoon, everyone. Today we'll be presenting the HighHeatFlux Thermal Management Project. Just some context, cooling is seen in electronic components in which there's a lot of waste heat that's generated. And so up here you can see how example of a group who's cooling a CPU and a GPU through a closed-loop cooling system with liquid nitrogen. And so that's kind of, and then in this picture you can see an electronics board that's getting heated up. And so thermal management is important because if you don't cool down certain objects and electronics that are hot, then they'll degrade eventually. So that's the overall context. In the background, I'm not sure why this is there, but basically, so we created a copper rod over here, and here, and essentially, so far they've been using water and a refrigerated bath system, and they've achieved a heat flux of 120 watts per centimeter squared. Our goal is to get to around 500 watts per centimeter squared. So that's our goal, and these are our objectives. These are some of our specifications that we are following. We're putting in about 1,000 watts of heat, and we're trying to dissipate 500 watts per centimeter squared. We're going to use liquid nitrogen. So this is our organization. This is our timeline. So far we've been testing in the fall with water. Winter we've been testing with liquid nitrogen. We're also creating a new rod, and in spring we'll be testing with a much bigger tank with more liquid nitrogen. This is our work downstream. Okay, let me see. Yeah.
So I'll be talking about the new copper rod design. So when designing the copper rod, we consider two things: material cost and machining cost. The thing is, we want to machine everything, which comes up to a budget of $455. Most of the costs came from designing clamps. And the clamp is going to be a 2-piece clamp. As you see on your right, there's 2 clamps. And the thing is, we hope to basically be able to clamp down the copper material and also have holes on the top part where we can screw into the holder, which is the top material over there. The two materials we're considering is stainless steel 304 and copper. The reason why I chose stainless steel is because of the high annealing temperature. It takes 1,000 degrees Celsius to warp that material. And the thing is, we're only getting up to around like 500 degrees, 600 degrees Celsius. So it's pretty hot, and it's able to maintain that temperature. For the second material, copper, the reason why I decided to pick up copper is because copper has a high thermal conductivity that allows high amount of heat flux through the material. That's what our goal of our project is, to basically get the most amount of heat flux to the material. And the total cost of this whole design is $539. That's a little much, but I think because the design is interchangeable, we're able to swap materials in and out if we need to. So in the long term, it will save us money.
So this is the installation chamber that we're designing for this quarter. And so we want to, it basically houses the copper rod and holds it in place as we're spraying this, I don't know the pointer, but as we're spraying this side with liquid nitrogen. And one of the faces screws into the pipe, it's threaded. And this is the cool side, so we can just use regular threading and use Teflon tape to wrap it around so it's not that hot. And the other side is the hot side, where the cartridge heater goes in, 1,000 watts. It's going to be around 500, 600 degrees. And so we can't really use Teflon tape on that side, so we're using MPT threads. Basically, it has a degree at which it goes in, so it seals itself. So we don't need any Teflon tape or any other components. All of this is made out of 304 stainless steel as well. And those holes are for thermocouple feed-throughs and for the cartridge heater, and those are made out of 316 stainless steel. And so we purchased materials. We purchased a Schedule 80 pipe, which is that pipe you see right there, and 304 stainless steel round bar, which will make up the 2 faces on each side. And right now I'm consulting with Mark at the research machine shop on getting a quote, and hopefully we can get machining done in a week or 2.
Okay, so this is our current tank that we have. It's pretty cheap per month, so we've been using this to do tests, and yeah, we haven't been able to get the pressure up. As you can see, it takes 8 hours to get to 4 psi, but we need to have at least 8 psi for it to operate. And then yeah.
What I did basically was I set the whole rod to an initial temperature of 100 degrees Celsius, and then I applied thermal load within the cartridge chamber, which is the upper half in red, with 100 degrees Celsius. We're trying to keep it constant, 100 degrees. And then the liquid nitrogen temperature of negative 196 degrees applied at the bottom. And this is basically the gradient temperature shown. And then so basically after you run the thermal analysis, you can apply a heat flux graph through SolidWorks. And so at node 1, which is this one below right here, we get a 258 watt centimeters squared. And then in the second node over there, a little higher up, which is closer to the heat, we get a lower heat flux, which is 220 watt centimeters squared. So we're pretty close to what the real data is presenting. And so what I did was I just took our insulation chamber and the rod that we're currently using for our tests to see how much heat will travel outside into the environment, see how much the metal or the material might yield the displacement of the metal, after doing all the simulation, all the temperatures are at a reasonable level where no material will melt, yield, displace too much. The only part would actually displace is the cartridge heater, but it would only displace like 0.13 centimeters, which is basically nothing at all.
This is our budget. We had Europe money this year, which is $1,000 that gave us. And every quarter we have like about 8 people who are joining, so I accounted for that over here. And so our leftover balance, we still have $700 by the end of this year. So these are